This is our lecture 3 of magnetic effect of current. Here, by the application of Biot law, we are going to obtain the magnetic field due to a long straight conducting wire. So in this picture, a wire is shown along the y direction. This is the wire, and the current is I is flowing in this long straight conducting wire. We have to obtain the magnetic field due to this current carrying conducting wire at a point P, which is at a particular distance OP, which is A, from the wire. It is the perpendicular distance of this point P is OP. To obtain the magnetic field at point P, let us a current element dl has been selected, which is at a distance L from the point O. This the current element is marked by yellow color. Here R is the position vector of the point P relative to the current element dl, and theta is the angle between the vector R and the current element dl, which is along the y-axis. We know from the Biot law, the expression of magnetic field P due to a current element dl is given by mu0 by 4 pi I dl sine theta by r square. Now to use this, from this figure we have dl, r, the angle between them is theta, I, the current is flowing through this square, so it is mu0 by 4 pi I dl sine theta by r square. Now here, to convert all these variable to a single variable and to integrate dB successfully, we are using this triangle and some trigonometry. From this triangle OPQ, we have here this angle is 90 degree, so angle theta plus angle phi is again 90 degree. So we have angle theta plus phi is equal to 90 degree. The phi is this angle OPQ and angle theta is OQP. And we know that from here theta is 90 degree minus phi. So we have sine theta is sine 90 minus phi, that is sine 90 minus phi is cosine phi. And from this triangle OPQ, we have cos phi. Cos phi is OP by QP. So cos phi is OP by QP. From here, OP is A and QP is R. So from here we have R is A by cosine phi, that is R is equal to A sec phi. So we have taken theta into phi and R into phi variable. And also from this triangle, we have tan phi. Tan phi is OQ divided by OP. So tan phi, we have from here OQ is L, that is the distance of this current element from O. It is L divided by OP. It is A. So we also have L is A tan phi. So if we take the differential dl, we have A is a constant sec square phi d phi. Now put the value of dl, the value of sine theta, value of r in terms of phi, which you have just obtained. And then we have mu0 by 4 pi I. For dl, we have A sec square phi d phi. We have putting the value. Sine theta is cos phi. It is cos phi. And r square is a square sec square phi. So we have obtained the value of dB in terms of phi. So from here we can see these two cancels out. 1a cancels out. So we have mu0 I by 4 pi cos phi d phi divided by A. So now to obtain the total magnetic field at point P, we have to integrate this one. So let us see. The total field at point P due to the entire conducting wire can be easily obtained by integration. Suppose here this angle is phi 2 for the upper part of this wire and This angle is phi 1. From this lower part, this angle are taken in the opposite direction. So to obtain B, the magnetic field, it is integrated over dV. The limits are minus phi 1 to phi 2. So mu 0 I, just put the value of dV here, and here mu 0 I by 4 pi a are constant, so they are taken outside the integration. So we have cos phi d phi, integration of from minus phi 1 to phi 2. We know integration of cos phi d phi is sin phi, and if we put the limit, sin phi 1 plus sin phi 2 will be there, the minus minus plus. So we have sin phi 1 plus sin phi 2. This is the general expression for B due to this long straight current carrying conducting wire, the magnetic field at point P. And if we use the right hand thumb rule and we hold the wire in such a fashion that our thumb is pointing towards the direction of positive y-axis, that is the direction of current, then the curl of our rest of the fingers will show the direction of the magnetic field, which is clearly shown. It is pointing into the page. So it is marked by a cross. This is the indicates that according to the right hand thumb rule, the direction of the magnetic field will be perpendicular to the plane of the page and into the page. Now we have some boundary conditions. If we have a wire of infinite length, the case 1, if the wire is infinitely long and the point P is near the middle of the wire. So if the wire is infinitely long, this phi 2 and phi 1 will be increasing, and their nearly will be 90 degree. And as we know, sin phi 1 and sin phi 2 for phi 1 and phi 2 90 degree, they will be 1. So from the expression, the general expression which we have obtained, we shall have mu 0 I by 4 pi a sin phi 1 plus sin phi 2. That is, they are 1. So 2 will be there. So B is mu 0 I by 2 pi a. So this is the expression of magnetic field due to an infinitely long current carrying conducting wire at a distance A. And now the case 2 is if the wire is infinitely long, but the point P lies at one of the end. Suppose this point P is at the end, one of the end of the wire. So this phi 1 is again, suppose it is here. So phi 1 again becoming 90 degree for an infinite length. But if it is at the end point, it is not extending in this direction, then phi 2 becomes 0. So this phi 2 becomes 0. So sin 0 is 0 we have. So from here we have B is, if we put the value, mu 0 I by 4 pi a. So this is for the case 2. So these are the expression of magnetic field for these two limiting cases. And as we have obtained the direction, we can say that if the current is flowing in the upward direction, as in our case, the magnetic field will be curled in this fashion, and it will be pointing into the page, and it is coming out in the left hand side, and it is going into the page. It is in the anti-clockwise direction. Now if we change the direction of the current in the opposite direction as compared to the first one, then this direction will also reverse. So the direction of magnetic lines of force due to the straight current carrying conducting wire can be easily obtained by using this.